Hi guys, this video is about vectors and three-dimensional space. We're going to talk about the three-dimensional coordinate system that we'll use in our class. We're going to discuss the fact that it's a right-handed system and what that means. We're going to sketch vectors in three-dimensional space and plot points. We'll talk about the midpoint formula and also the equation of a sphere. Now those of you that are taking my calculus class, your first standard is on vectors and vector operations. All of this on the three-dimensional coordinate system, this right here, is related to that standard, S4, which is on vectors. Vectors in three-dimensional space. I guess midpoint is part of that too. I don't believe I've ever put that midpoint formula on a quiz though. But the equation of a sphere, that is covered in our standard over surfaces. So keep that in mind. It is in 12.1 and 12.2 in your book, but it's not going to be on the quiz over this material. It's going to be on a different quiz later. Okay, so let's talk about the three-dimensional coordinate system. I always like to generalize. I like thinking about dimensionality. So one dimension, just like the x-axis. There's our 0, and it goes from negative infinity to infinity. Maybe that's all real numbers. Now in 2D, what we did was we took an x-axis that had all real numbers on it, and we intersected it with a perpendicular axis that we called the y-axis. This is all real numbers and this is all real numbers. So together, x could be any real number and y could be any real number. So it looks like that. We call it R2. That's how we read it. Now 3D is similar. Instead of having two axes that are perpendicular to each other, we're going to have three mutually perpendicular axes. Now, it's going to be difficult to see, difficult to draw on 2D paper. You just do the best you can. I'm not an artist. You're going to see from my graphs they're not great. But you do try to draw your graphs with a little bit of perspective. The z-axis points up. And the way we're going to draw it, the x-axis is pointing out from that. It looks like it's pointing out at an angle, but you actually want to imagine like there's a person standing here. Maybe that's me. See, that's how great an artist I am. Okay. And the z-axis is going in the direction of my torso. And the x-axis the positive x-axis, goes out directly in front of me. Like if I extended my right arm forward, that right arm is going to be parallel to the x-axis. And if you extend your, so you've got your right arm going forward, and then your other arm, your left arm, going to your left. So your right left arm is at a 90-degree angle from your right arm. You're going directly to the left. See, sorry, those are not arms. That's an arm and that's an arm. That's what I'm trying to show you. This is called a right-handed coordinate system. Now we could have done it the other way around. I could have put my left arm forward and my right arm to my right. That's a left-handed coordinate system. We're not going to look at left-handed coordinate systems in this class though. Most of the science and the physics and the math is all done in this right-handed coordinate system. Another way to think about this is to think about this as a room. Like if you're standing in the back corner of a room like this, I often do this when I'm in class. The z-axis is like that seam on the wall that's facing up. Maybe I've got a room. I'm standing in a room like this. The z-axis is in that back corner. The y-axis is behind me, and the x-axis is over here to my left. Now this floor that I'm standing on, that is part of, it's not the whole thing, but it's part of the xy plane. The xy plane is the plane that contains the x-axis and the y-axis. And its equation is z equals 0. So I'm standing at z equals 0, 1 unit up from me, that's z equals 1. So there's another plane, z equals 1, that would slice up from me, up there. And then z equals 2 is 1 level above that. I could have a whole bunch of planes, all just one level or one layered on top of another. I don't think that doing that with my hand is really helping on the computer. But this is z equals 0, and then there's one plane above it, parallel to it, and there's one plane above it, parallel to that. There's z equals -3, it's 3 units down. It's like the floor in my next door neighbor's apartment, for example. So that's the xy plane. The yz plane is like the plane back here. It's the plane that's behind me. Maybe if I'm teaching, it's the plane where my whiteboard is. This is the yz plane. And the equation of this plane is x equals 0. Notice in the yz plane, there's no x there, and I've got x equals 0. And in the xy plane, there's no z in this equation, and its equation is z equals 0. There's no coincidence in that. The missing variable, that's the one that's set equal to 0 over there. The xy plane is the plane that's behind me. And that other wall to my left, separating my classroom from the next person's classroom, like that's the xz plane. And its equation is y equals 0. Okay, so that's our coordinate system. That's what it looks like in 3D. And now instead of an xy plane only, we get an xy plane, which I'm standing on, a yz plane behind me, and an xz plane to my left. And these actually extend further because there is a negative x-axis not pictured here, and a negative y-axis back here, and a negative z-axis down here. We can go below this, we can go behind this. Behind that wall is where x is negative. On the other side of that wall to my left, the next classroom over, that's where y is negative. You can go downstairs, that's where z is negative. All of those things are possible. And this space that I'm in, where x, y, and z are all positive, we're going to call that the first octant. Remember back in algebra class, we said that that was quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Now I've got 4 octants up here where z is positive, and then I've got 4 more octants downstairs where z is negative. Different textbooks are different. Some of them I've seen label these 1, 2, 3, 4, and then start 5, 6, 7, 8 where z is negative below you. Some of them say the only one that's really labeled is the first octant. We're going to stick to that convention because the textbooks sometimes disagree, and that means I'm not really sure what the formal definition is. So I'm standing here in the first octant. That's our classroom. Positive z-axis is going up. The x-axis is that that boundary between the wall to my left and the floor, and the y-axis is the boundary between the wall behind me and the floor that I'm standing on. Okay, now we're going to talk about plotting points in three-dimensional space and looking at vectors in three-dimensional space. It's actually not too bad. I always feel a little bit like Bob Ross whenever I'm doing this. Let's say I want to plot the point x equals 3, y equals 2, z equals 5. Well, I know I want to go forward 3 units in the x direction. So I'm just going to draw tick marks like this. I'm drawing them on an angle because I'm imagining some perspective. I want to go 2 units in the y direction. And then I want to go up 5 units in the z direction. So I'm going to go over here, and then up 5. One way that I can do that is I can draw a perspective picture of a box that looks like that, where this is one of the edges of my box, and that's an edge of my box, and that's an edge of my box. So I'm going to use these tick marks at first, and I'm going to draw some lines. I'm going to draw a line that's parallel to the y-axis that goes out to y equals 2, and then one that's parallel to the z-axis that goes up to z equals 5. Like that's one end of my box. Like it's the back end. It's the farthest away from me. Now parallel to the x-axis, I want to go out to x equals 3 in the xz plane. It's a little bit harder to do. I'm trying to meet them both at the same place. So I've got parallel to the z-axis, I'm going straight up, and then parallel to the x-axis, I'm coming forward. Doesn't look exactly like it's forward, but think in perspective terms, it looks like it's coming forward. And then I'm going to do the same thing down here. Parallel to the x-axis, it looks like this. Parallel to the y-axis, it looks like that. That is the point x equals 3, y equals 2, z equals 0. But I want to go up to z equals 5. So I'm going to keep making my box. Parallel to the y-axis, parallel to the z-axis. See, it's not perfect. You can see it's not even quite parallel. But there we are. We go forward 3, plus 2 units in the y direction. Actually, forward 3 plus 2 units in the y direction, and up 5 units in the z direction. And we're located here at x equals 3, y equals 2, z equals 5. Now that's a point. Now if I want to plot the vector that ends at that point, that's the vector with components 3, 2, 5. Or if I prefer, I can call that 3 times I hat plus 2 times j hat plus 5 times k hat. Either one's fine. I've got it in component form and as a linear combination of our 3 unit vectors, one in the x direction, the y direction, and the z direction. Start at the origin and go out to that point. So this isn't a very useful picture. I don't really have a sense of what that vector looks like. But if I imagine that I've got a box that looks like this, and imagine that it's on the diagonal, it's going from that back corner to this front corner that's closest to us, and that's upstairs as well. It's up on the top layer. Then it can kind of help you imagine it. But without all these extra lines, it might not be clear what's going on with that vector. So I don't do a lot of graphing of vectors in 3D like this because it's not very insightful for me. It doesn't really give me any intuition about what's going on with the geometric problem. Now I mentioned I hat, j hat, and k hat. Let's put these on here as well. I hat, remember, that is the unit vector in the x direction. So it's 1 unit long, goes straight into the x direction. That's I hat. J hat is 1 unit long and it goes in the y direction. And k hat is 1 unit long and it goes in the z direction. So that one is k hat. So we got I hat, j hat, and k hat. This says the vector v is 3 times I hat. So I'm going to use a different color. I'm going to use this orange. 3 times I hat plus 2 times j hat, add tip to tail, plus 5 times k hat, up 5 units in the z direction. If I start where I started and I end where I ended up, don't I get the vector v that we started with? I hope you see that we do. It started at the origin and it ends right there at our point P. So yeah, v is the vector sum of these guys. Or you can think of this as just telling you, wherever you start, go 3 units in the x direction, 2 units in the y direction, and 5 units in the z direction. That's where the terminal point of v will end up from whatever that starting point is. So that's plotting points and plotting vectors. Now we talked about the distance formula. Distance in 2D or 3D was this. If I've got 2 points, x1, y1, and z1, and x2, y2, and z2, and I'm trying to find the distance between those 2 points, I just subtract the coordinates. I do x2 minus x1, then I square that, and then I do y2 minus y1, and I square that, and then z2 minus z1, and I square that. Then we want to add those together and take the square root. That's our distance formula. Now, when we're talking about a sphere is just a set of points. Well, it's a geometric object too, but it's a set of points, x, y, z, that are r units from a center point. So the distance between this general point in the sphere, x, y, z, and the center, x naught, y naught, z naught, is r. Well, I can use these. I can use these as my p and my q in the distance formula up there, and I can come up with the equation of a sphere. So the distance d is r, and I'm going to think of this as my terminal point, and that is my initial on my vector. It's going from the center of the sphere out to a point on the sphere. Let's draw it like this. There's x naught, y naught, z naught. Here's some point x, y, z on the sphere. It looks like it's on a circle. Here it's a sphere. Try to add some extra curves for dimensionality. That's the vector here. I want the length of that vector. The length of that vector has to be r. The length of that vector is r. And so I take the vector, which has components x minus x naught, y minus y naught, and z minus z naught. I square them, add them, and take the square root. So I square them, add them, and take the square root. Now square both sides and write it a little differently, and you've got the equation of a sphere in standard form. And I square both sides, I'm going to have an r squared over here. This is very easy to work with. If you're given a sphere in standard form, it's easy to look at the equation and read off the center and the radius. If you are given a radius and a center, it's easy to substitute those in here. One thing that you might need to review is how to complete the square. Sometimes we're given a sphere and all of these have been expanded, and it's a little less obvious what the standard form would be. But if we complete the square on the x, the y, and the z, we can write it like this, if it truly is a sphere. So we're going to look at a couple of examples like that. So let's say you've got x minus 2 squared plus y plus 4 squared plus z minus 1 squared equals, let's say, 4. All right, well, matching our patterns, If someone asked me for the center and the radius of this sphere, it would be easy to figure out. X naught, Y naught, and Z naught. Those are the coordinates of my center. They're just given by these three numbers. Now, because there's a minus in these formulas, it's going to have the opposite sign of whatever's there. If you see a -2, it's a +2. The coordinate is. I see a +4 there. Adding 4 is the same as subtracting a -4, so it's going to be the opposite sign, and the opposite sign of that is a 1. So that's our center. Careful here, the radius is not 4. The radius squared is 4. So we take the square root of both sides, and you get r equals 2. So this is the sphere centered at this point with a radius of 2. It's a little bit hard to draw, but if I wanted to, I could. First, I'm going to draw my center point. Go 2 units in the x direction, backwards 4 units in the y direction, up 1 unit in the z direction. My little rectangular box is not helping me because the y-axis is also dotted. I'm going to make that negative y-axis solid just so it's a little bit easier to see. But this is x equals 2, y equals -4, z equals 1. That's our center. And we want to go 2 units in all directions. So we want to go back 2 units to here and forwards 2 units to here. That's in the x direction. Left 2 units and right 2 units for the y. So we're going to go to -2. Oh, it's hard to draw. It's hard to draw. And then we're going to go up 2 in the z direction and down 2 in the z direction. Now do the best you can. You don't have to be an artist. If you're in my class, you can just draw something that looks kind of like this. And then be like, Miss Townsend, that's a sphere. I'll be totally fine with it. But the center should be clear. The center is 2, -4, 1. And then the radius, maybe I will just label my radius r equals 2 if I was trying to sketch this sphere. All right. So I could give you the equation and ask you for the center and the radius and ask you to graph it. Or I could say, find the equation of a sphere. The sphere with center 1, 2, 3 and radius 1. I'm just going to make the radius really nice and simple. So that's my x naught, y naught, z naught. I'm going to write down my equation. Oops. And I've got radius over here. Subtract 1 from the x, subtract 2 from the y, subtract 3 from the z, square the radius. Simplify, 1 squared of course is 1. Let's make that a -2. So then we'd have minus a -2. So we make that a plus. I just wanted to show you an example where that would happen. And then that's our equation. And we could graph it by plotting that point and then just drawing points. You want to go forwards and backwards r units, left and right r units, and up and down r units in order to find those points on the sphere. Now sometimes you'll see an equation like this, and they'll say x squared plus 6x plus y squared minus 4y plus z squared plus 2z minus 3 equals 0. Now I just made this up, so the radius is probably not going to be very nice, but they might tell you this is an equation. It may or may not be a sphere. Figure out what it is. If they did, what you would do is you'd group all the x's together, group all the y's together, and group all the z's together. This time it was kind of already grouped that way because I just made it up. And then move the constant to the other side. To get rid of the -3, we add 3 to both sides. And then you want to complete the squares. Make sure whatever you do to the left-hand side, you do the same thing to the right-hand side. So b is the number in front of the x if there's a 1 in front of the x squared, and there already is. If there was a 2x squared there, I'd have to factor out the 2 from both of these guys before I continue, but I don't have to. I'm good to go. There's a 1 in front of the y squared, so I don't have to factor. There's a 1 in front of the z squared, so I don't have to factor anything out. But if there were constants here, constants in front of those squared variables, you'd have to factor first before you do this. This is an example where I don't have to. So I find out what b is, take half of that, square it. 3 squared is 9. I'm going to add that to this side to complete the square. That's legal as long as I do the same thing on the other side. Then here, there's your b. Take half of it and square it. -2 times -2 is +4. Add 4 to complete the square. Make sure you add 4 to the other side as well. Identify your b. Half of b is 1. 1 squared is 1. Add 1 to both sides. All right, so now I got a perfect square, and a perfect square, and some arithmetic to do on the right-hand side. When you factor, you get that. I'm going to skip all the steps for the factoring because we're in Calc 3. Most people don't need that. If you do need that, that's okay. Just go look it up. And then we're going to simplify the right-hand side. That's 10 plus 7 is 17. All right. So that's my sphere. It's in standard form now. The center of the sphere, given by x naught, y naught, z naught. And remember, you're going to take the opposite of whatever sign is there, whatever is visible. So if I see a +3, it's going to be a -3. When I see a -2, it's going to be a 2. When I see a +1, that's going to be a -1. R squared is 17. So just take the square root of both sides. R is the square root of 17. It's a little bit more than the square root of 16. So it's a little bit more than 4. So I'd plot this point, and I'd go out 4 plus units in the x direction, y direction, and z direction in order to sketch my sphere if I wanted to. All right. Now the last part of this video is about the midpoint formula. So let's see, you've got 2 points in 3-dimensional space, x, y, z, and x, y, z. First point, I'm going to use subscripts of 1. Second point, I'm going to use subscripts of 2. You might want to know what that midpoint is. Question is, what is it? It's actually a very straightforward generalization of what you learned about midpoint way back when you learned it in 2D. The coordinates of the midpoint come from averaging the x values, the y values, and the z values. The x coordinate is the average x value. And if you have 2 test scores, you're trying to get your average, you just add them together and divide by 2, right? That's all we're doing here. To get the average y value, I just add them together, divide by 2. Average z value, divide by 2. Sorry for interchanging those. The order doesn't matter though, it's addition, so we're good to go. So that's how we find the midpoint. Generally, I don't see a lot of problems where I have to use this, but if somebody were to say, give me 2 points on the outside of the sphere, and I was trying to find the center, I could find the midpoint of those 2 points to find the center of the sphere, and then half of that distance from one point to the other would be the radius. So this really is just going to come up whenever you're looking at problems involving spheres. So that's it for this video. The next video will be about applications of vectors. So we're going to do some word problems and some problems in geometry involving vectors.